In last class, we introduced the idea of cis-trans isomerism in cycloalkanes. So chat with the person beside you. Which of the following compounds does not show cis-trans isomerism? Which one could not have a cis-trans isomer? Chat with the person beside you and submit your answer. So like, well,
The program you apply in summer of your spring, like during summer.
yeah, you can sign up for it at the beginning of second year or at the beginning of third year. And 10 more seconds. And 10 more seconds. And 3, 2, and 1. Okay, we're quite split here. Almost half went for E, which is the correct answer, which means E does not show cis-trans isomerism. So we have a cyclobutane here. Let's see why this is the case. This one chlorine could be a wedge coming towards you. This other chlorine could be a hatched line going away from you. And then we have to decide that chlorine, should it be cis to the chlorine coming towards you on the same side of the carbon-carbon plane, or should it be trans to the other chlorine, opposite sides of the plane? Well, all of the atoms are the same. Being cis to one chlorine, being trans to the other chlorine, you can't actually tell the difference. So if you build what you think is cis, what you think is trans, it's not cis or trans because you can't actually distinguish that. Now that's in contrast, let's just look at A. A could have both chlorines coming towards you. We built a cyclopropane last class and looked at the arrangement of the carbon atoms and how the substituents can come above or below the plane. We could draw it like that, and this would be the cis version. We could build it with one of them still coming towards you, but one of them going away from you. If you built both of those, you're going to see that they're different molecules. You can't interconvert between them by just rotating bonds. You actually have to break a carbon-chlorine bond and form a carbon-chlorine bond. So the two that we drew there for A, those would be cis-trans isomers, a type of stereoisomer. Any questions on that? We were quite split on that one. Okay, we saw this slide last class, but I'm putting it up again just to ground ourselves in our conversation today. There are different types of isomers. We could have constitutional isomers or structural isomers. These are different because of their connectivity. So if we have a methyl group, this is a CH3 group coming off of carbon 1, and a methyl group, CH3, coming off of carbon 2, this would be one structural arrangement. Or we could put that extra methyl group, move that one from carbon 2 to carbon 3, or move that methyl group to coming off of carbon 4. 1, 1, 1, 2, 1, 3, 1, 4, they all have the same molecular formula, but they have different connectivities. The substituents are arranged in a different order. These are constitutional isomers because they have a different connectivity. We could look at one of these constitutional isomers. We're going to choose 1,2-dimethyl cyclohexane. And we can also have stereoisomers from this molecule. We could have both methyl groups pointing towards you. That would be a cis 1,2-dimethyl. Or we could have one pointing towards you and one pointing away from you. That would be the trans 1,2-dimethyl. Those would be stereoisomers. And that's what we were building in this very messy example. We're going to try to make it a little neater today. So in this very long example, we are starting with 1,2-dimethyl cyclohexane. All of the molecules on this screen have the methyl groups on carbon 1 and carbon 2. Last class, we started with the 1,2 trans option. We started up here. One methyl group going up, one methyl group going down. We built that molecule, and then we saw that it could flex. It could do that flip-flop. We're going to do it a lot today. And we could make another conformation of the same molecule. The molecule on the top right here, it's the same molecule as the one on the left. It's 1,2 trans dimethyl cyclohexane. The top two molecules, they're just different conformations of the same molecule. One is more stable because it has both groups in equatorial positions, but it's the same molecule, the same isomer, just different conformations. Where we're going to start today, I have put the star, and that's what we're going to build. So follow along with me here. Grab your cyclohexane, and remember to make the chair conformation. You take your hands on opposite sides, bring it up like a boat, and then turn one side down. And then it sits beautifully on 3 prongs. So we're going to exactly build the bottom left molecule, the 1,2 cis, and I'm using red balls for my methyl groups. The 1,2 cis, I see an up axial position for my back methyl group. So I have an up in an axial position. The carbon next to it has an up methyl group in an equatorial position. So see how it aligns to the structure that we've made. Now I'm going to take this down portion, this down triangle, and I'm going to flip it up, and I'm going to take this up angling triangle and rotate it down. So once you have this built, follow along with me. This is my down triangle on the right. Watch this equatorial position here. So my right hand goes up, my left hand, the up triangle, goes down. You can set it down, and it's beautifully on 3 down prongs. This up equatorial is now an up axial. This up axial is now up equatorial. I'm going to flip once more. This is what we started with. Equatorial on the front, axial on the back. Flip, flop. Now it's axial on the front, equatorial on the back. We've done a conformation or a flip-flop. And then we can draw in the methyl group that was in an equatorial up position is now in an axial up position. The methyl group that was in an up axial is now in an up equatorial. I can see both methyl groups are still in up positions. So this one's up compared to the other substituent on that carbon. This one's up compared to the other substituent. So they're both up, so they're still a cis isomer. Of course, I could flip it over and see they're both down, down, but they're on the same side. So it's still the same molecule, 1,2 cis, but we have a different conformation. So we can analyze these 2 conformations of the same molecule, 1,2 cis, and we have to decide which one is more stable. Who says the one on the left is more stable? Who says the one on the right is more stable? Who says they're both the same energy? And I agree. They have the same energy because they each have one axial and one equatorial. So axial and equatorial, axial and equatorial. So both conformations have the same energy. So we would expect both to exist in similar amounts. One isn't more stable than the other. That's different than the 1,2 trans, where one was clearly more stable. And we would expect to find more molecules in the more stable conformation. Okay, so all the molecules that you have built on this screen are based off of the carbon 1, carbon 2, so 1,2-dimethyl. We've looked at 2 stereoisomers and 2 conformations for each stereoisomer. We're now going to move to 1,3-dimethyl cyclohexane. So we're going to break a bond. And now, we're going to count from carbon 1, 2, 3, and I'm going to put this in a position. We're going to start with the 1,2 trans. So if I squish this down and make the carbons all flat, it doesn't actually exist like that, but to make it really easy to see that one methyl group is above the plane of my carbons and one is below, it's just nice and easy that way. Okay, and then flip-flop your chair around until you can make it exactly match the picture that you see. So I'm going to flip-flop off the screen so I don't drive you crazy. Now I'm having fun with this. So we have an axial in the back and an equatorial in the front. So back carbon has an up axial. I'm going to say this is carbon 1, and then I'm going to count forward 2, 3. This is in a down equatorial position. So see if you can build your molecule to exactly match what you see here. So we have an up axial and a down equatorial. So play with it, try holding it up so that it matches perfectly. You might need to rotate to look from a different angle, flip it around, do a chair flex, or just exactly build it the way that you see it on the screen. Okay, so this is my 1,3 trans. I'm now going to draw the one on the right. I'm going to do my flip-flop, my ring flexing. So I have, in this structure here, I'll highlight it here, I have a down triangle and an up triangle. The up triangle I'm going to flip down. The down triangle I'm going to flip up. So down triangle, I'm going to flip up. Up triangle, I'm going to flip down. Now, keeping it in the same position-ish, my front methyl group is now in a down axial. My back methyl group is in an up equatorial. Axial became equatorial, equatorial became axial. So my CH3 equatorial down became my CH3 axial pointing down. My methyl group that was an up axial is now an up equatorial. So then I have to decide, well, which one is more stable? I have an axial and an equatorial, and an axial and an equatorial for my two big substituents. So we can see that they must have the same energy. I'm going to squish mine down. I have an up and a down. That tells me it's a trans. But now I want to make this into a cis molecule. So I am going to take one of my methyl groups and take it off of one option, one, what's that called? Orbital region. And we're going to put it on the bottom one. So now when I squish this down, I can see both of my methyl groups are on the same side. So they're either both up, or to match the drawing in your book, they can be both down. So we're going to go flip, flop, and see if you can make your chair conformation exactly match what we see in the picture. So I have a down equatorial and a down equatorial. So try holding this up in front of you to match your workbook. It's a really valuable skill to be able to use the model kit. Try flip, flop, and make it align. I will tell you, almost every year on the exam, when I'm reviewing it, I have to pull out my model kit and build it, because there are so many different manipulations that you can do to a molecule. It can get really tricky to do in your head. But if you build it and then you can manipulate it, it makes it so much easier. So practice building the molecule and making it match exactly as we see it here. So I have a down equatorial and a down equatorial. I'm going to take my up triangle, move it down, my down triangle, and move it up. And when we do that, we're going to see how this rotates. So my down triangle, I'm going to flip up. My up triangle, I'm going to flip down. Now we can look at our model. Are they in equatorial or axial positions? Hands up for axial positions. And I agree, they're both in axial positions, both in down axial positions. So on our screen over here, we get to draw in where these methyl groups are now. Down axial and down axial, which means the other locations are for the hydrogens. So comparing the energy, we have equatorial versus axial and axial. Which one's more stable? Who votes for this one being more stable? Who votes for this one being more stable? And the correct answer is, as you identified it, equatorial is more stable. Awesome. Okay, we have looked at 2 stereoisomers and their different conformations, so that we can now move to a final constitutional isomer. We're now going to break a bond and form a 1,2 dimethyl cyclohexane. So squish it down. Carbon 1, 2, 3, 4. So opposite carbons. We're going to start with the trans, so we want them on opposite sides. Then take your model kit, bring it to a boat, flip one side down, and then rotate it until it exactly matches the picture. The carbon on the left has the up methyl group. The carbon on the right has the down methyl group. Once you have that, we're going to take our hands. We're going to take this down triangle and flip it up, and this up triangle and flip it down. Before we do, what do you think is going to happen to the positions of these 2 methyl groups? Tell the person beside you. What's going to happen when we do the flexing? They're both in axial positions right now, so what's going to happen when we ring flex, when we go flip-flop? Well, let's try it. So we're going to take the right-hand side, come up, the left-hand side, come down. What does it look like? What positions are they in now? Equatorial. Show me your equatorial, your 1,4 trans with equatorial. Well done. And so then we can draw this in on our sheet. Okay, so a little bit of the challenge is figuring out how to draw it on our page. It takes some practice, but it's worth it. We can get there. So all the axial went to equatorial. All the equatorial went to axial when we did our flip-flop. Flip-flop, I'm back to my molecule in the top left. I now want to turn this into a 1,4 cis. In the picture on the screen, the carbon on the right has the down axial. So I'm going to take the one on the left, break that bond, form a new bond, which tells me I have a new molecule when I'm doing that. I have the same constitutional isomer. They're still off of carbon 1 and carbon 4. But now if I squish this down, you can see they're on the same side. So they're both down, down, or up, up. On our screen, we have them as down, down, so I'm going to flip like that. We want to go back to our chair, so we bring both hands up, one hand down to bring our chair conformation. So I have a down axial on the right, a down equatorial on the left. So our final flip-flop here, the down triangle goes up, the up triangle goes down. Predict what's going to happen before you do that. We have axial and equatorial. What do you think is going to happen? Take that down and flip it up. Take the up and flip it down. They're both still in down positions, but we now have equatorial and axial rather than axial and equatorial. On the left, we have equatorial and axial. On the right, we have equatorial and axial. So these have the same energy. We forgot to vote on the top one. So the top 1,4 trans, which one is more stable? Who votes for the one on the left? Who votes for the one on the right, on the top? That is correct. This one is more stable. Awesome. Okay, now that was a long example, but it's important because it walks us through constitutional isomers, stereoisomers, and conformations. So far, you have been drawing these molecules and just adding in the substituents. What's going to be helpful is if you have a very brief drawing class. So follow along with me while you're doing your homework. It's really helpful to know how to draw these molecules. We're going to draw a cyclohexane and add 1,2-dichloro in a trans position. Okay, so draw along with me. We're going to start with 2 parallel lines kind of stacked on top of each other. On the right, draw a down triangle. On the left, draw an up triangle. Then I want to turn this into a 1,2 trans dichloro. So I'm going to start with an axial chlorine pointing down. Doesn't matter which one I start on. But if that's carbon 1, one of the carbons next to it is going to have to be carbon 2. So I'm going to choose this one and put this in an up axial. They're on opposite sides of the carbon plane relative to where those other positions are. Now, drawing in the axial and equatorial is really helpful. So every second carbon is going to have an axial and an equatorial. I find it easy to draw in the 3 up axials and then to draw in the 3 down axial positions. Those ones are easiest for me to identify. Then you can draw in your equatorial positions. These ones I think are a little bit more challenging, but try to think of that up, down, continuing on. What's even better is if you have your molecule kit, your cyclohexane in that chair conformation, hold it up, and that can also help you figure out where to draw in the equatorial positions. So, an equatorial position, and down, and up, and down, and up, and down. If you start at 1 carbon and look at the axials goes up, the next carbon has axial down, next carbon has axial up, and so on. Same with the equatorial. It's up, down, all the way across. Okay, we're going to finish this drawing lesson. What happens when it flip-flops? Well, draw 2 parallel lines. In one of them, they were going this way. Now they're going this way. So 2 parallel lines on top of each other, but now they're oriented in an opposite direction. Once you've drawn those 2 parallel lines, we draw an up triangle and a down triangle. Then I find it's helpful to draw in my up axials, 1, 2, 3, and my down axials, 1, 2, 3, and then to draw in the equatorials. And imagine again the up, down continuing along here. Up, down, up, down, up, down. And then we can put in our chlorine atoms. Down and up. Okay, I was glad to see so many model kits today. Keep bringing it to class. I will see you on Friday. We're going to use our model kits again, so bring them out. All the best with the rest of your day.